In the previous lectures, we saw Fourier transform and how they affect LTA systems and how we can simplify convolution using Fourier transforms. Now, what if we know the impulse response and the Fourier transform of the impulse response, basically the spectrum of the impulse response? Can we say anything about the properties of the system just by knowing the spectrum of the impulse response? There are some things that we can comment, and the first thing that we'll talk about now is the invertibility. Remember earlier we said of all the properties, invertibility is slightly difficult to comment upon just by looking at the impulse response, because we said that if a system was invertible, then we should be able to find the function H inverse such that when you convolve that with your impulse response, you are supposed to get the Dirac delta signal. But how to find this H inverse was a question that we were not able to answer at that point of time, because it's a tricky thing to find an H inverse systematically given any H. But Fourier transform helps us to compute that. And how is that? Because Fourier transform converts a convolution operation into the multiplication operation, inverse is also very simple. So let us say that we have a convolution operation like this. Then what is the corresponding Fourier transform? So if you apply Fourier transform on both sides, on the left hand side we get the Fourier transform of H inverse multiplied with the Fourier transform of H equal to the Fourier transform of delta. So what is the Fourier transform of delta? We already saw that the Fourier transform of delta is just 1. So the Fourier transform of Dirac delta is just 1, which is very simple to work with. So if you want to find the inverse now, what do? It's very straightforward. You just take this to the other side and we get the inverse is simply the reciprocal of the spectrum of our system. That is as simple as that. So if you want to find the corresponding time domain representation, that is the impulse response of the inverse system, all you have to do is just take the inverse Fourier transform of the reciprocal of the spectrum of the original system. That's it. That gives you the inverse. Now, what if the system is non-invertible? If the system is non-invertible, then this reciprocal will not exist at certain points or at all the points. So for example, what if h of j omega is equal to 0? So if h of j omega is equal to 0 for, let's say, omega equal to some omega naught. For example, it is equal to let's say 10 radians per second. At 10 radians per second, if the spectrum is 0, what does that mean? Then the inverse system will not exist, right? What does this mean? If I had a phasor, let us say e power j omega naught t or 10 radians, and if I feed that as the input to my system whose spectrum is h of j omega, then what will be the output? We know what happens, right? So it basically says that for any frequency omega, the frequency response is given by this spectrum. So the frequency response to this particular frequency is 0. So basically you get output 0. So which means if I scale this, let us say by 2 times, the output is still 0. So now we have found out 2 different signals for which the output is going to be 0, and hence this becomes a non-invertible system. So whenever there is an omega value for which h of j omega is 0, then the corresponding LTA system is non-invertible LTA system. As long as this h of j omega is non-zero for all values of omega, then the corresponding system is invertible, and then we can find the inverse of this spectrum using the inverse Fourier transform, which gives us the impulse response of the invertible system or the inverse of the system. So this helps us to find out if a system is invertible or not, and if it is invertible, what is the inverse of the system. So Fourier transform helps us to find this in a very simple manner. Okay, so this helps us find the invertibility of the system. What about causality? So what are the other properties other than linearity and time invariance? The other properties are invertibility, causality and stability, right? So we'll see about that. So can we comment anything about the causality of the system? If the impulse response is not given but only the spectrum is given. If the impulse response is given, you know exactly how to find the causality. The impulse response should be 0 for all negative values of time, and that simply means causality. What if the spectrum alone is given? A very simple notion is that if the spectrum is band limited, if the spectrum is band limited like this, or something like this, or something like this, all these are band limited. So within some minus omega naught to some plus omega 1. As long as the spectrum is band limited, the uncertainty principle tells us that in time domain, the signal is going to extend from minus infinity to plus infinity, which means the impulse response will be non-zero for even the negative values of time. So any band limited system, which means the spectrum of the system is finite. It is non-zero only for a small region of frequency values. That is what we refer to as the band limited spectrum. So if the system has a band limited spectrum, meaning the Fourier transform of the impulse response of the system is band limited, then the corresponding impulse response will extend from minus infinity to plus infinity due to the uncertainty principle, and for this reason the system will automatically become non-causal. But the other way around is not always true. What does that mean? It means that given a system is non-causal, should the system be always band limited? That is not necessarily true. So we can also have a non-causal system where the impulse response is extending in the negative time and the spectrum is also extending from minus infinity to plus infinity. That is also possible. The other way around is not necessarily true. For example, if you take the rectangular function, let's assume that this is the impulse response of the system. So clearly the impulse response shows that the system is non-causal because for negative values of time there is a non-zero value of the impulse response. If you find its spectrum, the spectrum is going to be the sinc function, which means it's going to extend from minus infinity to plus infinity. Clearly this is not band limited. So a non-causal signal here has infinite bandwidth. Okay, so it is not necessary that any non-causal impulse response should have a band limited spectrum. Okay, so but any band limited spectrum will always have a non-causal impulse response. The other way around is true. So this is all we can comment about causality. So otherwise we cannot really comment about causality just by looking at the spectrum. So to be more precise, we can say if we split the set of all systems to be causal and non-causal, then a small portion of that is band limited. So a subset of non-causal systems is band limited. So anything that is band limited is present inside this non-causal, but anything that is non-causal can be band limited or need not be band limited. Okay. So what about stability? So stability means that we need to have the impulse response to be absolutely integrable. This is what we meant by stability. So if this is true, then we say that the system, LTI system, is stable. But this condition also comes up somewhere else when we talked about the existence of Fourier series, the convergence of Fourier series. So does that condition apply here also? If those conditions apply, then the first condition itself says that the signal should be absolutely integrable, which means even if the Fourier transform exists, then automatically the system becomes stable. So let us see that. So the set of Dirichlet conditions that we had earlier for Fourier series exists even for Fourier transform. So we can say that the Fourier transform, that x of j omega equals integral minus infinity to infinity x of t e power minus j omega t dt. When will this integral exist? When will this be defined and not infinity? So that is the question that we are trying to answer. So when will this be even defined? Forget about being infinity. When will this be even defined? Will it exist? That is what we mean by convergence of the Fourier transform. So the same Dirichlet conditions hold here. So we can say that the signal x of t must be absolutely integrable. Okay. If it is absolutely integrable, then for sure we can say that this integral that we compute here to find the Fourier transform, that will be also existing, that is, it will be finite also. The reasoning is the same. So we need to find the inner product. Earlier the inner product was the integral in one period. Now we are going to integrate it over the entire interval minus infinity to plus infinity, but still this is an inner product. So if that has to be finite, then we will say that x of t must be absolutely integrable. And the same conditions for the existence at the discontinuities also exist here. And the other conditions which talk about what happens to the Fourier transform when there are discontinuities also exist. So there must be only a finite number of maxima and minima in any finite interval. There must also be only a finite number of discontinuities in any finite interval. The same thing that we saw earlier for Fourier series, which ensures that the series converges at all points except some finite number of discontinuities, right? That is the same thing even here. So whenever there is a discontinuity, the Fourier transform will evaluate to a value which is equal to the average of the left and right limit. Same thing as what happens in Fourier transform, because whatever we have here at x of t is equal to 1 by 2 pi. Basically what are we doing? So we are taking the coefficients for the phases that we are going to add up. So what are we doing? We are just simply representing x of t in terms of phases with different coefficients, and because the phases are taking continuous value of frequency, we are going to integrate instead of summation. So everything on the right hand side is continuous. So if there is a discontinuity on the left hand side, then what happens at those points alone, the Fourier transform values will converge to the mean of the left and right limits. So if there are infinitely many discontinuities, then the convergence will not happen. So there is a problem. So what we say is, we'll assume that there are only finite number of discontinuities, and because there are only finite number of discontinuities, we can still say that this equality holds. And this is the condition for which Fourier transforms will exist, but this is only a sufficient condition but not necessary. What does that mean? It means that if the conditions are satisfied by a given signal, then its Fourier transform will exist. But there can also be certain other signals for which these conditions need not be satisfied, but still the Fourier transform can be defined. So this is only sufficient, but it is not necessary that these conditions should be satisfied by some signals for their Fourier transform to exist. For example, let us say that x of t is equal to sine t by t. This is basically the sinc function, or you can define like this. So we already saw, if this was the impulse response of a system, that system is not stable. Why is that? That is because if you compute this integral, this integral will actually go to infinity. This is not absolutely integrable. But we saw that by duality, we can say that the Fourier transform of this sinc function is in fact nothing but a rectangular signal. So we'll get a band limited signal, right? Some omega naught minus and some omega here. So this is what we saw earlier. So if this is the case where we have a signal we know which does not satisfy the very first condition, but we are able to define its Fourier transform, then it means clearly that Dirichlet conditions are only sufficient but not necessary. So you can come up with signals where these conditions are not satisfied, but still the Fourier transform will exist. But one thing that you have to note, does this mean that the Parseval's theorem is not satisfied? No, that is not true. If the Fourier transform exists, then the Parseval's theorem is always satisfied. So in this case, even though the signal is not absolutely integrable, when you compute the energy of the signal, that is finite. So this is a special signal. The sinc function is special because if you try to integrate it without this square, then the area will go to infinity, but with the square, the area will become finite. So the energy is still finite, which means Parseval's theorem will still be satisfied, so that will still work. So Parseval's theorem is always true, no matter what. But the absolute integrability can vary, and the existence of Fourier transform will vary accordingly. So just because a signal is not absolutely integrable, we cannot say for sure if the Fourier transform will exist or not. It may or may not exist. But if these three conditions are satisfied, then for sure you can say that the Fourier transform will exist. So then how can we comment about the output of unstable LTI systems? So the moment we say that a particular system is unstable, then can we find out the output of such LTI systems? So why did we even talk about all this Fourier transforms and Fourier series? We said that convolution is difficult. So we'll say that whenever we want to compute a convolution of this form, all we'll do is we'll just convert that into simple multiplication, and then if we want the signal in time domain, we'll just take the inverse Fourier transform. So we wanted to simplify our life, right? So what if this h of t is such that the system is unstable? Then can we define Fourier transforms? Can we use them? Can we say that it's just simple multiplication and then take the inverse Fourier transform? Can we find the output like that? So you cannot find the output like that if the Fourier transform does not exist. If the convolution results in infinity because it is unstable, an unstable system does not necessarily mean it will always produce infinity as the output. There could be certain signals for which the output is still bounded, right? For all those signals, we can still use this Fourier transform property. So as long as the Fourier transform exists for h of t and x of t, we can still use this relationship and we can find out the output. But for certain class of signals for which make this system to be unstable, then you cannot use Fourier transforms in those cases. So this is a drawback of Fourier transform, that for unstable systems, we will not be able to use these properties because unstable systems can produce infinity as the output, and in those cases, we will not be able to use these properties. Because of this, you need to be very sure if the system is stable. If the system is stable, then you can directly use Fourier transform. There are no issues because the Dirichlet conditions will anyway be satisfied. But if the system is unstable, then either it could be a case where the Fourier transform may exist, like this example, or the Fourier transform need not exist. If Fourier transform exists, then you can still use these properties. If the Fourier transform does not exist, then you cannot use these properties. So you have to be careful, check these case by case. So this is a drawback where if the system is unstable, then you cannot use these properties and then you cannot simplify convolution. So this is the reason why we will define another transformation later, what is called as Laplace transformation, which will take care of this particular problem. We will see that a little later. Now we will continue with this Fourier transform analysis. Now, okay, what if the system is unstable? So how many systems that we actually are worried about are unstable? So should we really worry about unstable systems? Why? Let me not worry about unstable systems, because in practice, what if I want only stable systems? I need not worry about unstable systems at all, right?